So the last exam, I did test you a little bit on directional derivatives. So let's remind ourselves about directional derivatives. Let me go ahead and write it for a function of 3 variables because the principles still apply, though I might be more likely to ask you it for a function of 2 variables. You got a function f of x, y, z. This textbook doesn't typically give the dependent variable a name, though when I personally do, I usually call it u. We got the gradient of f. This could be confusing because u is not a unit vector, u is just a variable name. Maybe I should call it something different, w. It doesn't matter. We don't even have to give it a name. The gradient vector for a 3-dimensional situation would be this. Of course, for a 2-dimensional situation, you would just have 2 of those. It is in general a function of x, y, and z, or x and y for a 2-dimensional problem. You could have a point P and another point Q, and these could be in 3 dimensions. And you might be asked to find the directional derivative at the point P in the direction from P to Q. You'd want to first figure out the displacement vector from P to Q, effectively by subtracting coordinates Q minus P as a vector. And then don't forget, you'd want to find a unit vector in the same direction. Now I'll use a u vector. That's v divided by its magnitude, which I'll go ahead and also remind you is v divided by the square root of v divided with itself. So the directional derivative then of f at the point P, which we could write as d sub u of f at P, it is the rate of change of f in the direction of u. And we do want to use a unit vector partially so the formula works out right, but partially so we emphasize that we're measuring how fast f changes for, you might call it, unit speed directions in the direction of the vector. So that's why intuitively it's important to use a unit vector. But as far as this formula goes, it's also important to use a unit vector so that this formula works correctly. Technically, if you want to get back to foundations, directional derivatives are defined using limits of difference quotients, just like partial derivatives are. And even in those difference quotients, you need a unit vector. But now what's new is, okay, by the geometric interpretation of dot products, this is the magnitude of the gradient vector times the magnitude of u times the cosine of the angle. But the magnitude of u is 1 because it's a unit vector. So this is just the magnitude of the gradient vector at P times the cosine of the angle between what? Between the gradient vector and V. V may not be a unit vector, but u is a unit vector in the same direction as V. The gradient vector could point in lots of different directions. Maybe off this way. Maybe if it's a 3-dimensional picture here, could be sort of coming out of the screen towards you there. That red vector that I just drew could be a really long vector, but it's almost coming straight towards you. Just for the sake of pretending. And the angle then is this angle. That's the theta. And so technically, if you knew theta, you could use this to figure out the directional derivative as well, if you knew theta, though you wouldn't typically know theta. More importantly, it emphasizes that the directional derivative is going to be maximized when the cosine of theta is 1, which will happen if theta is 0, meaning the gradient vector and V are parallel. And more than parallel, pointing in the same direction. In other words, the direction that the directional derivative is maximized in is the direction of the gradient vector at that point. Say that again. The direction that the directional derivative is maximized in is in the direction of the gradient vector. So if you were asked a question like that, in what direction is the directional derivative maximized, you'd say in the direction of the gradient vector, and you could write down the gradient vector at that point. In what direction is it minimized is when cosine of theta is negative 180 degrees, pi radians. Opposite direction is the gradient vector, in the direction of the negative of the gradient vector. You could also ask a question like this: in what direction is the directional derivative 0? It's 0 when the angle is 90 degrees, pi over 2, right angle. If that's a right angle there, then the directional derivative is 0. For two-dimensional functions, if your level curve looks like this and the function's increasing as you move up this way, the gradient vector is going to be like that. If u happens to be perpendicular to that, if it's tangent to the level curve, if that's v or u, then that angle is 90 degrees and the directional derivative in that direction is going to be 0. The instantaneous rate of change of the function tangent to the level curve is 0. Also in the opposite direction. If it were a three-dimensional situation and we're talking about a level surface instead of a level curve and a point P, the gradient vector is still perpendicular to the surface. U could be any vector in a plane tangent to the surface, the tangent plane actually, and the directional derivative would be 0. Okay, so some conceptual points that are worth emphasizing and maybe being asked about. Could you find the equation of the tangent plane? Sure, you could. You could use the linear approximation idea from exam 2. Will I ask you to do that? Probably not, because I got other things to test you on. But theoretically, you could figure out what that tangent plane is. So you could figure out all directions in which the directional derivative is 0 at that point. Well, where do we go from there? From there we went on to, I guess I got to go a little faster now. Chain rule, multivariable chain rule. The most typical form of the chain rule was when z was a function of x and y. Well, okay, this maybe not most typical, but this was one instance, and x and y were functions of t. And you can find the derivative of z with respect to t. And it was the partial of z with respect to x times dx dt plus the partial of z with respect to y times dy dt. Another example situation was when z depends on x and y depend on other variables, which in general we typically called u and v, though we did do examples where they were polar coordinates, r and theta. And for example, dz du is dz dx times dx du plus dz dy times dy du. And the way to sort of think of that with the diagram is you want to think about every path from z down to u. And there's 2 of them. And you multiply derivatives along the consecutive paths. These diagrams can be generalized to situations where maybe z depends on 10 variables, and those 10 variables each depend on 20 variables. Okay? And so you wouldn't want to draw such a thing, but conceptually speaking, the idea still holds that from the upper variable down to the final bottom variable that you're differentiating with respect to, you'd go through every path through the diagram from that top variable to the bottom variable. And I guess if you had 10 paths up here and each one of those had 20 down here, I guess there would be a sum of 10 things if you were just focused on differentiating with respect to one of the 20 variables at the bottom. It'd be a sum of 10 products. These things can be thought of in terms of dot products as well. For example, this one can be thought of as this dot product. And that is a useful thing to know sometimes because it can give it a geometric interpretation. Because this is really a gradient vector. And this is really a velocity vector. So you could think of t as t varies, you're traveling along a parametric curve through, say, the contour map of level curves of F. And you're wondering how does z change as t changes? You can give it a geometric interpretation using the gradient vector and the velocity vector of your curve. I spent a ton of time on that, but I did briefly talk about that. It's worth thinking about maybe for some examples. Make sure you just try some simple examples where you think about that. And make sure you calculate the answer and you confirm that it seems right. You could think about the geometric meaning of dot product. Length of that vector times the length of that vector times the cosine of the angle between them. You'd want to draw the level curves, use contour plot in Mathematica to help you see it. We did extreme values too. Optimization, both local and global. The local focused on critical points in the second derivative test with the discriminant. Does give you a local max or a local min or a saddle point. The global is where you were thinking about on closed and bounded regions. You have to think about what happens in the interior and along the boundary. And there's two methods for the boundary. Use the equation of the boundary, plug it into the function, or use the Grimes multipliers. Should be able to do both. And then the double integrals. I've got one sample exam on Moodle. I don't think I put the answers up. It's one of the other ones from exam 2, but different. Look at different problems except for the directional derivative problems on both. We can maybe also very briefly here look at Dr. Yang's exam 3 from last fall, just to see what kind of problems he put on. I have not looked at it yet. This is the first time I'm looking at it. His exam 3. Not that I'm guaranteeing mine's going to look like his, but just to see what out of interest. Computer gradient, computer directional derivative. Okay. Write a short word problem. I haven't emphasized that, so I probably would not have you write a short word problem. Find a normal vector to a surface. Okay, I didn't mention that. Have we emphasized that enough? You'd want to, you have had problems like that. That's more related to tangent planes, right? You got a surface. You want to find a tangent plane. Once you got the equation on the tangent plane, if you rewrite it, you can find a normal vector, ABC, based on the equation AX plus BY plus CZ equals D. Would be how you do that. And you could parameterize the normal line is what he's having you do there. I guess I didn't really emphasize that since exam 2. So probably not. A minimum problem, it looks like. I think this domain's an ellipse shape. Probably the Lagrange multipliers there is the best thing to use. Maybe I'll post that on Moodle. More linear approximations, which we emphasized a fair amount on last exam. So it looks like he didn't put any integrals on them. Okay, I didn't know that. Is this the right exam? This is our exam 3, right? Not exam 4. Okay, he didn't put any integrals on his exam 3, but I think, so it's like he was just not going quite as far on the exams, but as far as the schedule he gave me, he said to do integrals by now. So, okay. Mine will emphasize integrals more than his did. And probably no tangent planes and normal lines like his did. But I think I probably will put that optimization problem on Moodle and I'll write up answers for that one. Okay.